Yay! Hello, lovely humans! In today's episode, we are tackling the time-independent Schrodinger equation. All right. So we are going to kind of work backwards. We're going to start with the solutions to the most famous introductory problem in quantum mechanics, a particle stuck in an infinite well. Our particle is not getting out of that well. So I'll set up the problem definition for you, but we're going to start by looking at the actual solutions to this particular setup, and we'll talk about what those solutions mean and how we interpret them. And then, in the second video, we will actually dive into the mathematics of how we get that solution, or really set of solutions, hint, hint. But to make this more accessible for folks that are, maybe not physics majors, or for folks that are physics majors and are like, what the heck does this mean? I know sometimes the math can be really overwhelming. So I want to start by looking at the solutions to this particular problem and really building a solid understanding of what they mean. Cool. All right. So let's get started. And like all good mathematicians and scientists, we are going to start by being upfront about our assumptions. So the first assumption that we are making is that we are working with the time-independent Schrodinger equation. In other words, our wave function is a function of x, or a function of space only, and we're going to neglect time for now. The other thing that we are assuming, because we're dealing with probabilities, this second equation is called normalization. Basically what that means, and why I covered probability before we dove into the nitty-gritty details of the Schrodinger equation, is that when you sum up the probability density of a particle, you have to find the particle somewhere. So that's really what this equation is saying, is that it's with certainty, 100%, you must find the particle somewhere. And so, really quick aside, this wave function with these lines and then squared, that's called the complex conjugate. It deals with complex numbers. If you're like, what the heck is that? Don't worry about it. It's basically just like taking a number and squaring it. And that is the actual probability density of the particle. So just to reiterate, the wave function itself is the shape of the probability of the particle, and the wave function squared is the probability density. And what's really interesting is that even though we're making this assumption to kind of ignore time and say that, well, our equation is going to be independent of time, aka the wave function is independent of time, it actually turns out that the probability density that we get does not depend on time. So that's a good thing for our solution because it makes our lives easier. Okay, so now let's dive into this problem setup. What the heck is an infinite well? It's a well that we're never getting out of. So I will admit this does not actually exist in the physical world as we know it. But what's useful about things like this, and what's often done in physics, is to take a concept and break it down to the most simplest possible scenario. That allows us to actually solve the problem from the ground up and to get solutions that we can wrap our heads around. And oftentimes the solutions that we get are still applicable to much more complex real-world scenarios, but by having this solid foundation, it makes it a lot easier for us to understand those more complex scenarios. And that's really what we're doing with this infinite box. We're saying, okay, we're gonna create a scenario that allows us to have easy boundary conditions. Basically, we're saying, the particle must stay in the box. We're not gonna look for you outside the box. In fact, we're gonna make it impossible for you to be outside the box because we can. Because we're working in the world of chalkboards where we get to define the rules. And then we can solve our equation and get some solutions and then interpret those and apply them to more real-world scenarios. Okay, so that's a lot of setup for this problem. But basically what that means is that our particle is free to move about the x-axis in the horizontal direction like this between the sides of our box, which I'm calling 0 and a, where a is just some constant, some width of the box. But at the sides of the box, it would require an infinite amount of energy for our particle to escape. So you can kind of think about it like a ball rolling between two really tall walls. The ball's only going to be rolling on the ground. It doesn't have any sort of bounce or anything like that. So we're only dealing with one spatial direction. And it's impossible for our ball to escape because the walls are so high. And to make it impossible to escape, we just say that it would require an infinite amount of energy to escape this box. So our particle is stuck. And that means that the probability of finding the particle outside of the box is 0. This will come up later when we are solving the Schrodinger wave equation. But I'm going to bypass that for now and look at the actual solution. So when we solve the time-independent Schrodinger equation for the wave function, we are going to get a wave function that has the form like this. The wave function only depends on the x direction, and it equals root 2 over a, again, where a is the width of our box, times sine of n pi x over a. Woohoo! And so in this case, x is our only variable. So this tells us the shape of the probability for a given point in the horizontal direction inside of the box. And n can be any whole integer. So 1, 2, 3, 4, etc., etc., etc. And what's really interesting about this is that it tells us that there are actually multiple probability densities for our particle, depending on how much energy it has. N equals 1 is called the fundamental, or basically the lowest energy state that our particle could have. And then if our particle maybe has a little bit more energy, it would have a higher value of n. Okay, what does that actually mean? Okay, so let's look at n equals 1. The shape of the wave function inside of our box would look like this. But because that just is the shape of the probability, our probability density would actually look something like this. And so this is a little bit misleading because the height of the wave function is going to be this value here, so this is going to be root 2 over a. But the probability density is actually going to be much smaller because the area has to equal 1 as given by this. In other words, when we add up all of the possible probabilities for where we might find the particle, we have to find it somewhere. So when we add up all of the possible locations that it can be, the area under this curve must equal 1, or 100% of finding the particle inside of the box. And so what's really interesting is that you'll notice, I'm going to label the box. So, whoopsies, that's 0, and that's a. So the most likely place that we would find the particle is at x equals a over 2. That's pretty interesting, right? And that actually hopefully matches our intuition. So if we were to wait and let's say the ball was rolling back and forth between these two giant walls, and we took a bunch of pictures of the ball, and then we found the average location using those pictures, or maybe we had a detector that clicked every time the ball passed at a specific location, the most likely place that we'd find that ball is the middle, because it's going to be passing by that middle point more than it hits the ends of the box. It passes this middle point twice as much as it hits the ends of the box. And so that makes a lot of sense. Cool. All right. It's nice when our intuition matches up with the math. But what happens if our particle has more energy? Let's say for n equals 2. Ooh, interesting. Okay, so we still have our box from 0 to a. And then in this case, we were plotting the wave function, where this, I'm going to just write this in red. Oopsies, I'm going to run out of space there. So this is the wave function squared. Okay, so now for n equals 2, we are going to get a probability shape that looks like that. And you're like, what the heck does that mean? This is why we have the probability density. So that's going to look like this. And so again, the amplitude of the sine wave is going to be root 2 over a, and this would be negative root 2 over a. But the height of the probability density is going to be much lower because when we add up all of the possible places we could find the particle, the area under the curve again has to equal 1. But this is really interesting because now all of a sudden when our particle has a little bit more energy, it changes the probability of finding the particle. So now all of a sudden our particle is most likely to be found at either a over 4 or 3a over 4. That's pretty interesting. So let's look at one more. For n equals 3, we have our box again, 0 to A, and in this case, I'm going to try and draw them equal. So now we have a wave shape that looks like that, and the probability density is going to look something like that. And again, when we sum up the area under the curve, it has to satisfy that. It has to equal 1. And so the one other thing that I want to point out is that the points at which the probability density or the wave function equals 0, when, I should say, when this equals 0, then the probability density also equals 0. Those are called nodes. And if you have taken waves, or if you know a little bit about waves, that will be a familiar concept. So in this case, we have 2 nodes when n equals 1. When n equals 2, we have 3 nodes. I always think that this is really fascinating. So what this says is that it is a very, very, very low, if not 0 probability. I guess you would say it's a 0 probability of finding the particle at the halfway point in the box. So that's very interesting to me. What does that mean? And then in this case, we have 1, 2, 3, 4 nodes. And the location of the most likely place to find the particle would be here, here, or here. So the most likely place where we'd find the particle, or the little ball that's rolling back and forth, depends on this number n, which really equates to how much energy the particle has. The other thing that I want to point out is that this is related to the amplitude, and it makes sense because it is scaled by the size of the box. The bigger the box we make, the more stretched out this would look. And then this factor here is such that if you recall, sine of 0 equals sine of pi. Can you all see that? A little bit. I'm writing really tiny. Okay. Sine of 0 equals sine of pi equals 0. And so when x equals 0, this whole thing equals 0. So that gives us this node here. And when x equals a divided by a cancels out, and you get an integer number of multiplied by pi, which is what gives you this node here. So as n increases, you're always going to have the wave function equaling 0 at the ends of the box. Pretty cool, right? Okay, so let me know if you have any questions about the solutions of this or the meaning. It is pretty weird, very bizarre, but that's why quantum mechanics is awesome. Not exactly intuitive. Okay, so check out part 2 to see how we actually get this solution. Yay for math, woohoo! See you in part 2, bye!